Events. Events are like logs. They can be used to obtain information about the actions taken by your smart contract. And we looked at events, and let me just pull this up real quick. Let's see all of this. So if we go to scan a good tool, look at a transaction that interacts with a smart contract. You see the logs here. And then if it emits an event, don't see it, don't see it. Well, you can trust me. If there is events, then there it's event logs. Yeah. So then here you see an event. Yeah.
Shark NFT. Your sponsored ads. They've got you nailed.
I'm sure there is. So to use to access the logs, they're part of the transaction receipt. So remember when we submitted a transaction that modified the state, you got not back the return value, but really the transaction receipt. And within that transaction receipt, you will see the events that are emitted. And events can be, you can also specify an indexed a keyword so that the event is indexed by that value and can be searched. Okay, so then I talked about that a contract does have context available that pertain essentially to blockchain. So there is a message sender. So this is essentially who initiated the contract call. There are some nuances there depending on how a contract was called. You can call a contract from another contract using call or delegate call, and then the context is a little bit different. But generally, when a contract gets invoked, message sender will be who initiated the contract call. You're able to access the gas price. You're able to access block context like the block hash, block timestamp, things like that. Now, one thing, again, to remind you of is these variables can seem like a source of entropy, like a source of randomness, like the block hash, right? You could just say, hey, I'm going to take the last X bytes, and that's my random seed variable, right? It is not truly random because these variables are controlled by, and now the validator, right? So if you ever need randomness, you should use an oracle that generates randomness outside of the chain and makes it available to you. Then you have an address object, and within that address object, you can get information about the balance. Now, the balance here is only native Ether. It has nothing to do with ERC20 balances because those are handled by the ERC20 contract. Address also allows you to send Ether through the send function. So that's how you would, like, let's assume a contract has a function that wants to send, Ether to somebody else. You say address send value. There's also some built-in functions, kind of hashing functions, primarily self-destruct, and then this is the instance of the smart contract. So SmallC is the Solidity compiler that compiles Solidity into bytecode. So when you compile the .sol file into bytecode, it will also create the contract ABI. So did you guys already compile contract code with your environment? And so you see the two files that are being generated. the bytecode, and then the
So it's in the middle.
ABI file.
Oh, yeah.
And then, as I mentioned, it's good practice to verify your contract on Etherscan for easy consumption and verification. And this is much better than just relying on open source, right? You could say, hey, my protocol code is over here in GitHub, but there could be sync issues, right? Where essentially that code is really not what is deployed on chain. And so the only way you can really verify that is by taking the code, compiling it with the same version of the compiler and comparing it to what is on chain. So you can do that manually, or you can do it through Etherscan, and then it gets that green check mark.
For that, so like if I have a GitHub repo and I have a pipeline that's pushing and I want to do all that kind of stuff, then
It has the Etherscan API allows you to verify. Yeah. So then the ABI defines the functions in the contract that can be invoked and describe how each function will accept arguments and returns its results. And so remember earlier when we talked about the kind of the visibility, whether it's payable and whether it writes or reads state, that is then essentially defined down here, right? So this is payable false. It is a view function. So if you call it, you wouldn't have to pay transactions because transaction cost because it only reads state, and then it is a function. And then it takes, this is the name of it. It takes two inputs, one input, the owner of type address, and then it returns the balance of uint 256. Again, the ABI is only available if you make it available on Etherscan or you make your source code available so people can compile it themselves. If you don't have the ABI, you don't know the interface of the smart contract. So it's going to be very difficult for you to invoke it. Similarly, the ABI defines the events that the contract emits. Again, just a reminder, they can lie. And here you see also whether it's indexed or not, based on the keywords that you specify. Now, one thing that I did not, let me see whether I have this. Okay, I forgot to include one slide. So what happens if you invoke a contract with a function selector that does not exist? Right. So there's a special function that you can define called a fallback. So think of it, basically, there's the switch statement at the beginning of the contract. It basically compares your function hash with the function hashes in the contract. And then if none of it matches, then the fallback function gets invoked. The fallback function, if it is not implemented in your contract, I think the contract will revert. I think we already kind of covered that. Oh, so, okay. So how do you invoke a smart contract? So we already know from an EOA, you create a transaction and you submit that transaction again with a function selector, a function hash, and then your parameters. And then when you do that, you obtain a function receipt. You don't return get the return value. But if you call from another contract, you have two options. You can either use call or delegate call. And then when you do invoke the function, then you do get the return value back. When you invoke a contract, it is atomic. Either all the state changes are made or none, or it reverts with an error message. It is not a separate transaction. It is in the context of the existing transaction. So think of like the EOA invokes contract A, and now contract A could call contract B, and it can do that either through call or delegate call, but it's all part of one transaction.
Contract, my contract has to make another transaction for another.
It's all one transaction. Good question. Okay, so then the function selectors we already talked about, but just a refresher. So essentially, a function selector is the first 4 bytes of the Ketchak hash of the function signature, which is essentially the name of the function along with the types of the parameters. So let's say attack uint 256. Here I don't have, in this particular example, I don't have the any parameters, so it's empty.
So this in this case is just
Data then will send the function hash plus the parameters. Just show you once again. So here we have a transfer function with 2 parameters, and then if you look at it in the original, here is essentially the function selector. Oops. Here is, oops, God. Here's the first parameter, and then here's the second parameter. And then the way what happens when a function gets invoked, and if you run through a debugger, which you will have to do for some of the Ethernet challenges, you will see kind of how that works. There's data manipulation that basically from the input field kind of extracts those 4 bytes. And then there's essentially a gigantic switch statement where it basically compares those 4 bytes with the static 4 bytes that are encoded in the smart contract bytecode. And if there's a match, then it will jump to the implementation of that particular function. That's how function invocation essentially works. And there's a link here that if you're really interested in the details there on exactly what memory gets copied around, I recommend that particular article. Okay, so then as I mentioned, there's the message sender, and you are able to send there's an address, and you're able to send Ether to that address. And you can only send Ether to a contract if it is a payable function. The way to transfer Ether, there's 3 different ways. So one, you can call transfer, and you specify the value of Ether in way. And what that does, it only sends 2,300 gas. And if it fails, it throws an error. The send function also only sends 2,300 gas and returns a Boolean that you basically would have to check whether it was successful or not. So if you send using the send function and it fails and you don't check the value, then there may be some unintended consequences. And then lastly, you can send Ether using the call function. And what that does, it forwards all the gas, and this function returns a bool. So why do you think there's all these different mechanisms, and why does it only send 2,300 gas versus forwarding the gas? So there's okay, so there's two aspects, how the error gets communicated. So Duke said if you want to make sure that the entire state gets rolled back, then you want to use the first one because it will throw an error and everything gets reverted back. If you want to have more flexibility, then you use kind of the Boolean approach, the send function. Gas, exactly what Colin said in terms of so there's no new transactions that gets generated. It's just a continued execution of the transaction. Now, this only really becomes interesting in context of sending Ether to a contract, right? Because now that contract will continue the execution and it will require gas to do so. Now, if you want to give that contract, you know, a lot of rain in terms of what it's able to do, then you want to send a lot of gas. But if you're concerned about it kind of executing a whole bunch of state that wastes essentially your transaction fees, then you want to limit the gas that you pass along. Okay, so then Lego. So interacting with other smart contracts. And so you have a contract and you now want to call another contract. And there's, again, a variety of ways you can do that. So you can create the contract yourself. So let's assume you have the source code, then you just kind of instantiate the contract, and then you can call functions on it. The big advantage of that approach is that you have complete control. You know what the code is. The alternative way to do it is you have the contract code, and now you cast a deployed contract to that instance. In that particular instance, you know that the contract adheres to the interface, but you have no idea about the implementation. So you're putting a lot of trust into the address that you're casting. Now you can mitigate that again by looking at the verification check on Etherscan. But if the contract is not verified, then you have no idea. And then you have two low-level options. You can either do the call invocation, and what happens there, the context changes. So you have contract A calling contract B. What happens now, the message.sender variable will be set to contract A. So the context changes. Whereas if you do a delegate call, the context does not change, and contract B will execute with the same context as contract A. So in the example of message sender, it would be the invoking EOA. And also there are some issues around essentially local storage variables where contract B now essentially has access to the some of the same storage slots. Gas considerations, so auto gas exception. So let's assume you have a contract, right? You give it, let's say 10,000 gas, but it consumes 15,000 gas, then it will create an error. And raising that error with auto gas exception. Now, of course, all the gas that was spent is gone, right? And so when you call another contract, and again, depending on how you call it, you may pass along the gas that you have, and now you're entrusting that contract to handle that gas responsibly. And so avoid calling other contracts, or if you do call contracts, specify the gas that you are willing to give that contract to execute. This is also particularly important if you're dealing with contracts that are immutable, meaning they implement the proxy pattern, right? So a contract may behave very well today, but then it gets upgraded and may behave poorly down the road, right? Sending versus withdrawing. So let's assume you have a contract, an airdrop contract, and you now want to send tokens to everybody. So I could send, I can invoke that. I basically have a list of addresses, and I say send token, right, to every single address. Maria gets one, Duke gets one, Andrew, Mark, Colin, right? Everybody gets a token. That means that smart contract would have to call send 5 times, right? And that every send costs gas. And if you now have thousands of addresses where you want to do that, eventually you will run into the gas limit for the particular block. So this is not a great pattern. The other aspect is, you know, who I'm sending a token to could be an EOA, or it could be a contract that then, you know, runs additional code. So there's some risk involved there as well. And so the better pattern is to make the tokens available and then use a Merkle tree to determine who has access to the tokens, or who gets tokens, and then ask people to essentially withdraw the token. So they would come to you, they would pay the gas cost, as opposed to you, the contract owner. Any questions on anything we covered today? The first is graded assignment. So this is an analysis task. And you're able to use any of the tools that we discussed last week. Etherscan, Dune, Luabase. You can use the Web3 API if you want. And so the assignment is about understanding a particular attack in greater detail. So on August 19th, the Curve Finance protocol fell victim to a DNS hijacking attack. So think of their dApp front end, right? So I'm a user, I want to use Curve, I go to curve.xyz. That brings me to their dApp. But what the attacker essentially was able to do is to hijack the DNS such that when you go to Curve XYZ, you go to a website they control. And then what they did, they inserted essentially, as the user interacted with the dApp, they essentially popped up a transaction in their wallet, right? MetaMask basically says, hey, do you want to sign this transaction? And that transaction called the approval function on their ERC20 tokens that the wallet owned and provided that approval to the attacker. And so then the attacker was able to call the transfer function to transfer the tokens from the user's wallet into the attacker wallet. Make sense? And so what you would see on-chain are a set of transactions that basically from a user that grants token approvals to the attacker. And then you would see a transaction from the attacker that moves the ERC tokens from the user's wallet into the attacker's wallet. And so for this assignment, I would ask you to create a timeline of the on-chain activity, as well as estimate the number of digital assets that were stolen, along with the digital assets that were at risk of being stolen. So the ones that are being stolen means essentially the attacker transferred them out of the wallet. And the digital assets that were of risk means the attacker had approval to move the assets, but didn't transfer them. And what I would ask you to do is create a Word document or Google Doc document that kind of outlines your steps, including screenshots and any code that you or queries that you used. Along with the final results, that basically is a timeline. When did it start? When did it end? And kind of the steps in between, as well as a table that basically contains the information about the digital assets that were stolen and the digital assets that were of risk of being stolen. Yes, sir. Rec.news is a great site that basically gives you information about attacks. So here's the Curve Finance attack, DNS hijacking, and basically down here, it will give you the starting point of the attacker. And the attacker had an EOA address as well as a contract. And so you would have to consider both of them. August 10th. Did I say 19th? Oh yeah. Okay, sorry. Good eye,
No,
Mark.
that's good. Okay, cool. That was my main question was like, okay, I'm pretty sure I need a contract address to start with.
I mean, token approvals can happen to an EOA and as well as a contract. Yeah, I would assume they use the contract, but I would double check both.